lecture 11.4, in which we talk about directly drawing with pixels. So everything we've done so far involves calling predefined functions like rect and ellipse and so on that act in a relatively abstract way. We don't have to worry about the details of how they actually draw the objects. But of course, there's obviously something going on at a lower level. When we call the line method, for example, to draw a line, there's an algorithm that has to calculate which pixels are in or out in order to represent the line in its best form. The version I was taught at university was called Bresenham's line algorithm, and I suspect it's still used under the bonnet of processing. And most of the time that's fine. We don't need to know the details of how the ellipse function works, so long as it produces what we want. And that's good engineering practice. But as computer scientists, it's useful for us to take a look under the bonnet, as it were, and delve a little bit deeper into the internals of how these things work. So in this way, first of all, we understand the algorithms better. They're not just black boxes. But secondly, if we ever have to actually write anything similar ourselves, then we'll know where to start. So we can directly access the pixels on the drawing canvas using the pixels array. So if we set one element of that array to a specific value, then we're essentially bypassing any drawing methods and writing directly to the canvas. Now there's a slight complication in that pixels on the canvas are stored in a linear array. So we need to work out how to go from an XY coordinate to a position in the linear array, an index. And we'll talk about that shortly. But for now, let's just look at a simple bit of code that creates random grayscale noise. And this is all on Blackboard. Okay. So in order to get direct access to the canvas, we first need to load in the pixels from the canvas, which copies them into the pixels array. And we do this, unsurprisingly, using the load pixels method, which essentially just sucks in all the pixels from the canvas into the pixels array and allows us to then access them. And here we basically loop over the entire linear array of pixels from 0 to the length of the array minus 1. So remember, we don't know in advance necessarily how big it is, so we simply say loop I start at 0, so long as I is less than the length of the pixels array, increment I. So this is basically saying for every pixel I, we pick a random value between 0 and 255. Okay. Now, this is, so just before I go on, remember if we choose a single value for a colour, like the background for example, if we just use a single value, then processing defaults to grayscale. Now we see this illustrated here, and this is new because we're using a new class, the colour class, which is supplied with processing. So basically a colour object, C in this case, wraps up the integer RGB values for the colour plus a transparency value. So previously we've been specifying the R, the G, the B as separate integer variables, and what a colour object does is basically wrap these three things together up with a transparency value into a single object. So it's essentially just a little bag of integers, and each pixel is effectively a colour object. So every pixel in the pixels array is an instance of the colour class. And as I just said, if we create a colour object with just a single value, in this case the random number between 0 and 255, then it defaults to setting its colour in grayscale from 0 black to 255 white. So all this is saying is basically create a temporary object C, which is a colour object in the grayscale range 0 to 255, which was randomly selected in the previous line. So this will repeatedly create a brand new temporary object C, which is then copied into the pixels array. So every time around this for loop, we're creating a brand new object C, okay, and giving it a random color, which we've just selected here. So every time around the loop, we're creating a brand new object, which is then copied into the pixels array. So then we just basically copy it in and then call update pixels, and that just tells the system that we're finished dealing with the pixels, and it essentially just does a refresh of the canvas, okay, with the new values. So now we know how to directly write a color to a specific pixel on the screen. But how do we visualize this in 2D and convert from a set of coordinates to a linear position in a pixel array? So we're used to thinking, when we're thinking about graphics, we're used to thinking about a grid of positions. So how do we convert from this two-dimensional grid to a linear location? So say we want to deal with this particular pixel here. How would we find its position? How would we find its index in this linear array? Well, we assume that we know that the width of the canvas, so we can sort of visualize the canvas, if you like, as a series of horizontal slices that are then laid end to end to form the pixel array. So what's the algorithm for going from x, y to index in the linear array? And if it helps, have a think about a specific pixel, like this one here, for example, which is at 0, 1, 2, 3, 0, 1, 2. So it's at 3, 2. Okay? X equals 3, y equals 2. Try and work out what the formula would be for getting from that xy coordinate to the position in the array. Pause the movie and have a think. Well, another way to visualize this is as the pixel map being a sort of cinema seating plan. So we go down a number of rows and then in to our seat. So the pixel is down a certain number of rows, the y, and then we add some indent, if you like, for the column or the x. So each row is width pixels wide, in this case 5. So we need to go y times width. So y iterations of width, if you like. So this is one iteration of width, 1, 2, so we go 2 plus 3 plus the indent. Okay, so we need to go y times width to get to the correct row, and then add on the x. Okay, so here's a worked example for 3, 2. So we go down 3 rows, so 0, 1, 2. Remember, it's 3 rows, but we start indexing at 0. So we go down 3 rows, 0, 1, 2, and then in 4, 0, 1, 2, 3. So that's in 4, 0, 1, 2, and 3. So the general formula for mapping from x, y to linear position in the index is essentially y times width plus x. Okay, y times width plus x, or x plus y times width. So if we plug the example values into this equation, then we get 3 plus 2 times 5, so 3y plus, 0, 1, 2, 3 for the x, plus y times 5, which is 0, 1, 2, and that gives us 3 plus 2 times 5, which is 3 plus 10, which is 13. And you can see here, that's the index in the linear array. So, here's a problem. Imagine that we want to directly write to the pixels on the screen to get this sort of stripy pattern. That is, without using any of the draw functions. So we don't want to be explicitly drawing white and blue lines. We want to basically make every other column on the canvas blue or white, so depending on its column. Based on what we know about how we directly access the pixels of the canvas, what's our algorithm for this? So pause the movie and have a think. Well, here's what I think we do. We loop over every column, then within each column we loop over every row. We basically scan from across slowly. So within each column, we then scan down and then move to the next column, scan down, move to the next column, scan down, move to the next column, scan down, and so on. So we very slowly inch our way across the canvas, but every time we hit a column, we then scan down the column. Okay? We then, at every scan point, if you like, we calculate the position, the pixel position in the linear array, and if the column is even, then we set the colour to white. Otherwise, if it's odd, we set the colour to blue. And then wherever we are, we set the pixel, the current pixel, to that colour. Okay? And here's the code. And it's on Blackboard as stripes. So we load the pixels, then we iterate over the columns, and then within that we iterate over all of the rows. Okay, we then calculate the position in the pixels array of the current pixel that we're looking at. Okay, so it's columns plus rows times width. Then if the current column value is even, that is, remember we can use the mod operator to say divide by 2, and if the remainder is 0, then we're in an even column, so set the stripe colour, if you like, to white. Otherwise we're in an odd column, so set the colour, set the pixel to blue. So here we basically say the pixel is white if we're in an even column, otherwise the pixel is blue if we're in an odd column, and we iterate over every row, and then we move to the next column. And once that's all finished, we simply update the pixels again to do the refresh. So this is just a reminder that we can use the mod operator to see if a number is even or odd, and if the remainder of dividing it by 2 is 0, then it's even. So how can we tune this code to get stripes of varying widths? So here we've got, so by stripe I mean the distance between the white lines. Okay, so this is a stripe, this is a stripe, this is a stripe, and so on. And what we're essentially trying to replicate is what I think is the best ever football shirt, which is this 1980s Ipswich Town home shirt, which is, I think, officially the best football top ever made. What variable do we need to tune, if you like, to be able to change the width between the white lines, between these lines here? So how do we change the width? Pause the movie and have a think. What do we need to add? Well, the distance between the white lines is determined by the value that we divide the column number by, the denominator. So the bigger the denominator, the wider the stripe. So if it's divided by 2, then it's every other column. If it's divided by 3, it's every third column. If it's divided by 20, so if it's C mod 2, then it's every other column. If it's C mod 3, then it's every third column. Every C mod 20, it's every 20th column, right? So this, rather than hard coding a value in here, 2, we can make this a variable, stripe width, say, if we want to call it that, and that value will tell us how wide the stripes need to be. So here's the code with the addition of the stripe width variable. So instead of hard coding the value 2 in, what we've done here is say if C mod stripe width is 0, that is it's a multiple of the stripe width value, then we draw it as white. Otherwise we draw it as blue. So we can have stripes as wide as we like by simply changing this value.